and that's not. Throw this here. Okay, so this is Piazza's up, and I don't know if it's hard to see, but anyway, you should have received a link. If you haven't, there's a link on CCLE. You can just kind of click this and follow through. This is important. Please make sure when you create your account that you use your first and last name, okay? Because Piazza is not like integrated to CCLE or anything like that, and so for you to get your participation points, I asked Piazza to kind of print out a report of student activity, and all they have is the name that you provide them, and so if the name you provide them doesn't match what I have in my grade book, I'm not able to transfer the grades over, okay? Or because it's just I'm inputting it manually, but I'm just kind of using does the name match? So you can just basically set your name settings with the little gear in the corner, and just make sure it's your name, okay? As you become curious about how many contributions you've made, there's this button right here that says statistics. That should be somewhere near the top, okay? And things that count as contributions are if you ask a question, if you answer a question, if you write a follow-up discussion comment or something like that. Basically, anytime you write a sentence and you submit it to Piazza, that's going to count as a contribution, okay? Please do take a moment and search to make sure your question hasn't already been asked. And if you need to refer to an old post, you can kind of hover over the top left corner of the post, and it will say something like type at 7, and that's kind of like the link to the older questions and stuff like that. Okay. You're always allowed to post anonymously, but I like it when people use their names, and then you can recognize oh, this is the person who's been answering answering questions, and this person has always, I don't know. You'll learn your classmates, right? Do you guys know the people sitting next to you right now? Why don't you guys turn to the person to your left or right and say, "Hi, I'm Miles," or what? Use your name, of course. So. Okay, all right. Let me get your attention back. Yes, I do want you guys to meet each other and stuff. But I saw a meme somebody posted, and it's the way they stored their contacts in the phone book was girl with curly hair or something. Cute-ish, whatever guy, whatever. Okay, anyway, you should know people's names, right? That's how we identify one another, names and faces. Okay. Anyway, we'll continue on our discussion on data structures, and on Wednesday we covered the one-dimensional data structures, the atomic vector, and the list, and the factor, which is kind of a special case. And now we'll enter into two-dimensional structures. So the first, or higher dimensional structures, I should say. And so the first thing is the matrix. Okay, the matrix and array are basically atomic vectors that have a dimension attribute associated with them. So let's say I create an atomic vector. Here, let me make this a little bit bigger for you guys. All right, whoops. I don't know if that's better. Okay, so A is an atomic vector, 1 through 6, okay? If I ask, does A have any attributes? Attributes of A. What will this return? It will return null, okay? There are currently no attributes associated with A. They don't exist, okay? So if I ask, does A have any dimensions, what will this say? The dimensions of A is also null, okay? So A has no dimensions right now. All right, we can create a matrix. I'll call this B, and I can go matrix 1 through 6, and we'll say the number of rows is 2, and the number of columns is 3, okay? And so when we ask for B, it looks like this, okay? 1, 2, 3, 4, 5, 6. They fill them down the rows first and then across the columns. If I ask, what are the dimensions of B, what will we get? Well, if somebody asked you in words, what are the dimensions of B, you would say 2 by 3, right? And that's exactly what we get. Okay, when you ask what are the dimensions of B, it says 2 rows, 3 columns, 2, 3. Okay, and if we ask what are the attributes of B, B has one attribute, and it's the dimensions, and they're 2 by 3. Okay, so those are the attributes of B, and that's it. And that's really the only thing that distinguishes A from B. Okay, if we ask the structure of A, it's an integer vector 1 through 6, and if we ask the structure of B, it's integer also 1 through 6, and the only thing that's different is that it's got 2 rows and 3 columns. Okay, B is basically an atomic vector with dimensions associated with it. All right. I'm going to go ahead and I'm going to just illustrate that. I'm going to delete everything out of my environment. Okay, so A currently doesn't exist, but we'll take 1 through 6 and make A out of it. Okay, and then all I'm going to do is I'm going to say the dimensions of A, which are currently null, I'm going to take the dimensions of A, and I'm going to say, I'm going to assign the value 2, 3 to the dimensions of A. All right? And when I do this, A becomes a matrix. Okay? So, and that's it. And you can also, and so if we ask what are the dimensions of A, it's 2, 3. The attributes of A is this, and A is identical to the matrix B that we created earlier. Okay? You can also take A, which is 2 by 3, and you can say the dimensions of A, I want to make 3 by 2, and it does that as well. Okay, and if you want to turn this back into an atomic vector, you can just say the dimensions of A, we are going to make them go away, and A turns back into an atomic vector. Okay, so matrices are just atomic vectors with a dimension attribute associated with it. Okay, and that's it. But if you try to change the dimension attribute of A using something that is not correct, such as 2 by 4, this will produce an error. Okay, because 2 by 4 would require 8 elements, and we only have 6. Right, and so it says I can't do that. I can't do that. Okay, so A is currently one-dimensional, or not one-dimensional, is an atomic vector with no dimensions associated with it. What happens if I say the dimensions of A is going to be 1 by 6? What happens here? What will A look like when I print it out? It's now a matrix, okay? 1 row, 6 columns, okay? So it's, and we ask, you know, is it a vector? A is no longer a vector, okay? Because it's got dimension attributes associated with it, okay? Whereas, and if we ask what are the attributes of A, it says the dimensions 1 through 6, and again, we can kill the dimensions, and we get this, and if we ask, is it a vector, then it's true, okay? Is all of this okay? All right, so we showed you some of this here. We created a matrix, 1 through 6 with 3 rows and 2 columns. Here we've created an array. An array is the same thing, except the dimensions, you've got more than 2 dimensions. So a matrix will have will have rows and columns, so you have 2 dimensions, and then an array will have, you know, basically length, width, depth, I don't know, things in hyperspace and stuff, right? Like that, right? So in this case, it's a number of rows, 2 rows, 3 columns, and maybe 2 sheets, if you want to think of it that way, or 2 layers, okay? And then after that would be kind of like the number of prisms or cubes, and then after that would be the number of hypercubes. I don't know, however you want to do this, okay? So, and when they fill out the numbers, they fill out according to the order of the dimensions. So it fills row-wise first, rows, columns, sheets. So row-wise first, so it goes 1, 2 down the rows, and then it goes across the columns, 3, 4, 5, 6. And once one sheet has been filled out, or one layer has been filled out, then it goes on to the next sheet, okay? And again, down the rows, across the columns, until the entire sheet has been filled. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, I think I've demoed this where you have a vector and you modify the dimensions in place, and it just changes the appearance there. We can ask for the length, okay? So, so here A is a vector 1 through 6, and I can ask what is the length of A, and it will say 6. If I ask how many rows does A have, what will this say? Number of rows of A. What is this? It's null, right? There's no rows because there's no dimensions associated with it, okay? Same with number of columns of A, null, okay? As soon as I turn into a matrix by saying 2 by 3, okay? Then I can ask how many rows does A have, and this will say 2. And I can ask how many columns does A have, and it's 3, okay? Just curious, okay. And you can actually look up and see, you know, the function n column, all it's doing is it's asking what is, you know, when it's the function of x, it's asking what is the dimensions of x, and give me back the second element in the dimensions of x, okay? And the number of rows, the function of number of rows is just what's the dimensions, and give me back the first element there, right? Because when we ask what are the dimensions of A, it gives me back a vector, 2, 3, and so number of rows just says, what's the dimensions? Oh, 2, 3, give me back just the first one, okay? So if the dimensions don't exist, number of rows is not going to exist either. Okay. All right, so there's A. Number of rows is 2, number of columns is 3. What is the length of A? It's 6. It's the length of the underlying atomic vector. Okay, so the atomic vector has 6 elements in it. It's a integer atomic vector with dimension attributes associated with it. Right? Is A atomic? That's true. Is it a vector? This is false, okay? Because it's got dimensions. Type of? Oops. What's the type of? Integer, right? Because the way we created A, if we look back, was we said A was basically 1 through 6, and then we associated some dimensions with it. And it also says it's up here, integer up here. You can give your row names and column names to a matrix also, okay? So we can say row names of A will be will be capital A and capital B, okay? And when I do that, now we have this, and we can ask for we can do column names of A similarly. And now we have column names. All right, what are the attributes of A now? We have dimensions, and now we also have dim names, okay? We've got dim names 1, which will be the rows, and dim names 2, which will be the columns. And we saw this. The length of A is 6, the number of rows is 2, and the number of columns is 3. Similar for B, which is the array. We can give the dimension, the dim names, different things like 1, 2, ABC, and AB. And again, this will correspond to the row names, the column names, and the names of the sheets. And you can see them appear here. Okay, so the dimensions of B is 2 rows, 3 columns, 2 sheets. What are the fourth would be number of cubes, and after that, I don't know, hypercubes or tesseracts or whatever. Okay. We can combine things, okay? So C is the function we use to combine vectors, okay? And that will generalize to binding column-wise and binding row-wise, okay? So we have C bind for binding across columns and R bind for binding across rows. You can also transpose using T, and you can also ask, is it a matrix or is it an array? Okay, so we have A here. A looks like this, and you can bind A and A together, and it will get that. And you can bind A and A row-wise, and you'll get that. Okay, so all it's doing is just C bind binds them like this, and R bind binds them like this. Okay. When you bind using R bind, so here's A, and I'm going to create another one called D, and we'll just change the column names of D to be X, Y, Z. Okay. So here's A and here's D. Okay. You can R bind these things together. and it will just ignore the column names of D. Okay, and it just takes them and sticks them together. Okay, and obviously if you C-bind them column-wise, then it will preserve the column names there. I've got a typo there. One-dimensional matrices and arrays. So we saw this a little bit earlier. Let me just delete everything out. A is an atomic vector here, has no dimensions, but we can say the dimensions of A are going to be 1 by 6, and we have a column. We can say B is 1 through 6, and the dimensions of B is 6 by 1, and so we have one row across here and one column, and these are still one-dimensional data structures. Okay, and if we ask on the atomic vector, the structure looks like this. It has no attributes, okay, because it's got no dimensions there. When we create a column matrix, okay, so all we've done is we've taken the thing and we've made a column thing. When we ask the structure looks very similar, okay? Structure here and the structure here. What's the difference between the structure of the atomic vector and the structure of the, here, let me just kind of do this over here. We'll call G will be just the atomic vector, right? So here is G and here is A, and here is D. Okay, or B. All right. So if I ask, what's the structure of G being the atomic vector, and the structure of B being the column thing, the only thing that's different is what? Is this comma 1. Okay, indicating that we have 6 rows in one column, and the row matrix looks also similar, but it says 1 row, 6 columns. Okay, and A and B they print differently, and G prints like this. Okay. What are the attributes of G? None, right? There's null. No attributes of G. Attributes of A, you got dimensions that say 1, 6. Attributes of of B is you got dimensions 6, 1. Okay. Now here's the thing that might be a little bit more confusing, is that we can create an array, and I'll call this, I guess I'll call this C. And so I'll take the elements 1 through 6, and I'll just give it, normally I would say, how many rows, how many columns, and how many sheets, or something like that. But here, I'm just going to give it one thing here, okay? And this is what C looks like, okay? Does C have any attributes? It does. It's got a dimension, and it's just got 1. It just has the number of things here, okay? It's funny because when you ask for G, G and C look like they're the same, okay? The attributes of G is null, whereas the attributes of C is, it does have dimensions and 6. Okay, C is technically an array of 1 dimension. It's a one-dimensional array, which feels like it should be an atomic vector. But the way R views an atomic vector is that it's an atomic vector with no attributes, no dimensions, whereas C is an array that has a dimension attribute. So if I say is.vector G, that will be true, is.vector C, that's going to be false. And there's a subtle difference when you ask for the structure. The structure of G, which is our atomic vector, looks like this. The structure of C, which is our one-dimensional array, looks like this. All right, and it says it's 1 through 6, but it is a one-dimensional structure. Okay, even though when we print them out, they look the same, but the underlying structure is different. Okay. All right, is that okay? So that's matrices and arrays. And so now we can talk about data frames. And so matrices and arrays and those atomic vectors, they're all atomic, meaning everything in these things have to be of the same data type, right? So G is an atomic vector. If I say in the fourth element of G, I want to stick in the letter F, or even if I just say the number 0, then G gets coerced into a string vector, right? Same thing with, C looks like this, and if I say I want to stick into there, then everything gets coerced into strings as well. Okay, still a one-dimensional array. And then A being a matrix, same with the matrix, except for this, I would have to say 1, 4. I want to stick in a string there, and then everything gets converted into characters. Okay. Yeah.
How do we create arrays?
How do you create a what?
An array.
An array?
Yeah.
So I mean, there's a few ways. You can just take a vector and then apply dimensions to it, or you can use the command array, and you take your vector 1 through, we'll say 1 through 64, and we want 4 rows, 4 by 4 by 4. Okay, and there we go. And then now we have a cube. Is that okay? All right. Okay, but anyway, so those structures were all atomic, meaning that they are homogeneous in that everything has to be of the same data type. Data frames allow us to carry different data types, right? And so the one-dimensional structure that was heterogeneous was what? The list, right? The list allows you to carry numeric values and character values and things like that. And a data frame, same thing. It allows you to have numeric values and character values, factors and things like that. So this is very useful when you're doing data collection, because a lot of times when you collect information on a subject, it's not going to be all numeric data. You might ask for their age and their height and their gender and, I don't know, whether they're a freshman or transfer student or whatever, or what major they are. And some of those are numeric and some of those are categorical. And the data frame allows you to kind of mix the types, okay? The important thing is that in R, a data frame is built on top of a list, okay? And so it uses the list as for its ability to carry different data types, and all it does is it just reshapes the list to be in the form of a rectangle, okay? It just takes the list, which used to be one-dimensional, and it turns it into a rectangle. And so what it requires is that the list, the elements of the list, those vectors have to be the same length. So you can have a list of a character vector with 10 elements and a numeric vector with 10 elements and another numeric vector with 10 elements. Then it will turn that into a data frame with 10 observations and 3 variables, 3 columns. Okay, because the original list has 3 variables or three things in it, and each of those have 10 elements. Okay, so the data frame can be treated like a one-dimensional structure where it's going to behave like a list, or it can be treated like a two-dimensional structure where it's going to behave like a matrix. So the way we make a data frame is we just call data.frame, and you can give it variable names. Data.frame, x is 1 through 3, and y is a, b, c. And it creates the data frame right here, just like that. Go ahead and okay, so here's my data frame like this. We can ask what's the structure of the data frame. And it says we've got 3 observations and 2 variables. The variables are x and y. And x has the integer values 1, 2, 3. And y is a factor with levels a, b, and c. Okay, and that's because the data frame's default behavior is going to turn character data into strings, into factors. So if you don't want that, just redo the thing with strings as factors false. Okay, and it looks the same, but when you ask, oops, the structure of it, we notice the difference here, right? It says integers and factor up there. After turning strings as factors false, we have integers and characters. Okay. Again, the underlying thing of the list, so when you print the data frame, it looks like a data frame, but you can kind of force it as to print like a list, and it looks like this. Okay. So it'll print out the x and it'll print out the y, and then and it also carries the class attribute that it's a data frame. So if you ask R the type of the data frame, it's going to say it's a list, whereas the class, it says it's a data frame. And by being identified as class data frame, that allows it to print nicely like this when we look at it. But it is good to keep in mind that the underlying data structure is indeed a list. And so and then you have the is.dataframe question. And so I'll just kind of cover some of the ways that we can create a data frame. Is that you can just turn things into a data frame, such as a vector will create a data frame with 1 column, whereas a list will create 1 column for each element in the list, but all of those elements, they need to be of the same length, and if not, it's gonna cause an error. Okay, and if you have a matrix, it'll just turn the matrix into a data frame. So let me just kind of show this kind of stuff. I've got A will be an integer vector, and if I say make a data frame out of A, then it creates a data frame here. Okay, so I can say dfa is going to be this, and data frame A looks like that. Structure of data frame A is it's a data frame 6 observations of 1 variable. Okay, so that's easy. Here, we'll make a list. We'll call L, and this will be a list, and we'll have a few things in here. So L will have X. We'll throw in the integers. We'll go backwards, 6 through 1. We'll have Y, which will be the letters, lowercase letters, 11 through 16, and Z will be capital letters, 6 through 1. Okay, so L is this, okay, 654321, and KLMNOP, and FEDCBA, right? And so here, it's very easy. We can just do data.frame L, and it makes a data frame out of it, okay? And that's very easy. DFL will be data frame of L, and we are happy. DFL looks like that. The structure of this data frame that we created out of L is this. Maybe we didn't want them to be factors. So when we do the creation of the data frame, we'll just say strings as factors is false. DFL looks almost the same, but the structure of DFL will maintain its character data as character data. Okay. However, if list L, we'll call this L2, will just be a copy of L. And in L2, $y, how do you delete an element out of, like let's say I wanted to delete that M. What's one way to do it? Okay, so here's M. The third element in L2y is M. All you have to do is you just kill it with null, okay? And you just say, oh, you can't, oh, it's not gonna let me do that. I'm sorry. All right, never mind. I thought I could just kill it this way. I guess sometimes you can't do that. All right, so I'll just have to, we'll take the first two elements. L2, I'm sorry, L2y subset, and we're just gonna do everything but the third element. Okay, so that'll work. L2 $y now has no M. Okay, so L2 looks like this. The structure of L2 is, you know, six elements here, 5 here, and 6 here. And so if I try to data frame this, okay, it throws an error. It says the arguments imply different numbers of rows. Okay, one of these things has 6 and then another has 5. Yeah, question.
Can you transpose a data frame?
I think so. Let's see. Okay, so we got DFL here. Transpose DFL. Yeah, it does it. So the transpose is a matrix operation. So what it does is it turns the data frame into a matrix, which means it's going to coerce everything into characters, and then it transposes it. Okay. So I think it'd be the same thing as DFL if I did as.matrix DFL here. It does this, and then transposes this. Yeah. Okay, so that's doing that. Oh, and then lastly, if we have a matrix, so we'll create a matrix using matrix 1 through 12. Number of rows equals 3. All right. So here's the matrix. And we'll say column names of M will be the letters 12 through 15. No, 12, 13, 14. Yeah, okay. So M is that, and so M is a matrix, right? Is that it's an integer matrix, and then all you have to do if you want to take that, you just data frame, throw the matrix into a data frame, and it looks very similar, but this is now a data frame. Okay, the structure of DFM is it's going to say it's a data frame. So here's the matrix with named columns, okay, and the structure of that says it's a matrix, and over here we now have a data frame with 4 variables, and these are the elements in those 4 variables. Okay. We can combine data frames using cbind and rbind. When you use cbind, okay, the number of rows have to match, otherwise it's going to throw an error. And when you combine data frames using rbind, the number of columns have to match and the names of the columns have to match, okay? So it's kind of just like you're adding additional observations to the data frame that you have. And so, you know, if earlier you have 50 observations where you've collected the age and the gender and the, I don't know, hair color or something like that, when you add, like let's say you're going to add 10 more observations using rbind, you need to have those same variables collected. Okay, otherwise it's going to throw an error. If you want to just take vectors and throw them into a data frame, just throw them directly into the data frame. Don't cbind them first, okay? So if you cbind them first, so here we have a vector and we cbind it with another vector, what's that going to do? I've got the integers 1, 2 and the characters A, B. If I cbind those together, what happens? It's going to coerce everything into characters because cbind will produce a matrix. And so if you take vectors and you cbind them as the first step, that's going to coerce everything into the same level as if you were using combine. And so that'll produce a matrix, and then you throw that into a data frame, you know, you're going to have some issues there. Just throw it directly into the data frame. Just take your vectors and throw them directly into the data frame, and that's fine. There's no need to make a matrix first. There's something called a table df in dplyr and the tidyverse. And this avoids something that's annoying where R will try to print the entire data frame and will or maybe like at least the first 1,000 rows of a data frame, and will flush out your entire screen output. And so dplyr, the tidyverse, and the tibbles, they are aware of how big your screen is and will only print what will fit, which is really nice. All right, we've got a few minutes left, and so I want to cover just a few things in subsetting. We'll get started here, and we'll wrap up subsetting probably next week. And so anyway, subsetting is used, is at first we use it to just kind of pick out certain elements from a larger data structure. So, you know, you've got a vector of 100 elements and maybe you only want 10 of them, 10 of the elements out of there. Subsetting is a way for us to do that. But R's subsetting things are super powerful, and you can do even more than just selecting, you know, 10 rows out of 100 or something like that. Okay, but we'll start off with these basic things. So here is an atomic vector, X. It's got 4 things in it, and the values are 2.1, 4.2, 3.3, and 5.4. And those numbers were selected so that they're not already in order from least to greatest, but you are able to see that 2.1 is the first element, and 4.2 is the second, and 3.3 is the third, because the number after the decimal place is the position in the original vector. So just because when I subset these things, it just creates a new vector and you're not quite sure what the original things were. So anyway, you can just give R a vector of integers. Say I want the third and first element, and it will pull out the third and first element. Okay. There's a function called order, and it will give you the indices that you need to use to get the elements in order. So if you ask for the order and you subset based on the order, it will sort them. Doing this operation is silly because we do have a function called sort, and it will sort them. But sometimes you just want to know like which value was in second place. You can just get the second element out of order, and that's going to be the third element. Okay. If you give the same number multiple times, it will pull that number multiple times. So if you say 1 and 1, it'll give you that first element twice. And if you give it decimal values, it will just truncate those numbers and return the thing. So if you give it 2.1 or 2.9, it's just going to pull the second element. Now, you shouldn't give it decimal values as a way to subset. But I don't know, you might do something weird later on. And the way numbers are stored on the computer is not according to mathematics. So sometimes you'll get a number and you think it's the number 3, but inside the computer it's actually 2.999999. Okay? And when it prints it, it's going to print 3 on the screen. But it's not actually 3. It's stored as 2.99999 in the computer. And if you were to use it in some operation like this, it's going to truncate the 0.999999 and pull out the second element, and you'll be confused what's going on. Okay. Negative integers says I want everything but that negative number. Okay. So you can say, I don't want the third and I don't want the first element. Then it returns the second, fourth. But you can't mix negative and positive things because then it gets confused. This thing, subsetting using logical vectors, is very important to understand. And it basically will return the elements where it is true and will ignore the elements where it's false. So here, true, true, false, false will return the first 2 elements, which are true, and ignore the third and fourth elements, which are false. Okay? And thus this statement, x greater than 3, is going to return a logical vector of trues and falses, where it is true just for this statement where x is greater than 3, and it will return those elements only. Okay? Still got another minute here, you guys. And so if the logical vector is shorter than the I consider this fairly rude to just get up in the middle of a lecture, but whatever. Okay, if the logical vector is shorter than the vector being subset, it will be recycled. Okay, and so if you have true, comma false, which has only 2 elements, it's equivalent to recycling it, getting true, false, and it will just pull out the first and third elements. Okay, anytime you're subsetting with an NA, you're going to get back NA, okay? A few special cases, if you have nothing, it returns everything, which is incredibly useful for subsetting a matrix. You might say, I want the first row, and you specify nothing for the columns, it will return all the columns in the first row. And subsetting with a 0 will return a 0-length vector. Okay, and then if things are named, you can subset using the names of those elements as well. So if you have a named vector, you can subset using the names. Okay, we'll end here for today, and we'll see you guys on Monday. Have a great weekend.